In today's class, we'll talk about a new data structure called as hashing. As you can see from the definition itself, hashing can be used to build, search or delete from a table. In a way, till now we have seen different types of data structures, like we have seen an array, we have seen linked list, and we have also seen binary trees, binary search trees and AVL trees, and also we have the concept of stacks and queues. So these are the different ways of storing the data. So why do we try to store data in different formats is, our main intention is time taken to search an element, search for some particular data element, insert a new element or insert a new data item, or increase or decrease the size allocated to the data, or deleting some part of the data, or deleting some part of the data or some element. All these such kind of operations should take less amount of time for us. So for this we have tried different types of data structures. Initially we said that we store data in the form of consecutive memory locations, and we call them as an arrays, and array index starts from 0 and so on and so forth. Array has some disadvantage, that is, if you don't use dynamic memory allocation, the size of your array is fixed, and during runtime you cannot increase or decrease the size of your array. Then and also searching takes more amount of time if the array is not sorted, that is, you have so for that what we have done is we have come to another data structure called as linked list. In linked list we said that the memory is allocated during runtime, that is dynamic memory allocation happens, and every node remembers the address of the next node, every data remembers the address of next data. So and main advantage of linked list is we can easily increase or decrease the size of the list, and we can increase it as and when we required, we can delete it as and when we do not require the memory, and also we have seen variations in this linked list, that is, we have seen circular linked list, doubly circular linked list and so on. And in doubly circular linked list, what happens is insertion, deletion, searching, all the operation becomes easier when compared to arrays. Then what we have said is, using this concept of linked list, we have modified the linked list and we made some variations, some modifications, and we came up with the concept of trees. We said that in tree data structures, searching an element, finding the minimum element, finding the maximum element, all such kind of activities, all kinds of operations takes even less amount of time when compared to linked list. So we talked about binary trees, binary search trees and AVL trees. Then we talked about specific type of data structure called as stacks and queues. In real time they are used by your operating systems, your programming languages for recursion. So for recursion purposes stack is used, and your operating system uses queues for managing the processes. So stacks and queues have some specific purposes assigned to them. So all these data structures, what do you mean by data structures is different ways of storing the data, and we try to find an optimal way of storing the data. And we also study all these data structures because based on application we can use any one of them, based on the application which you are trying to develop, based on that we can use any one of them. And the basic idea and basic motto is we have to find a kind of best data structures which takes less amount of time for searching an element or searching for some particular data, insertion, deletion, incrementing the size, decrementing the size of the allocated data. Okay, so deleting the elements. So all these operations should take less amount of time, and for that we have studied all these data structures. And one such data structure is hashing. In your hashing, let us first understand what basic idea behind hashing. Assume that you have an array. We will be using an array for implementing the concept of hashing, and obviously every array has some index number associated with them. Usually in an array, index starts from 0 and ends at n-1. This is the fixed index for us, and in a regular array we store that in the similar way. But here what do we do is, given a key element, we pass this key element to a hash function, and output of this hash function will be the index at which this key has to be stored. Okay, so we'll see what is this hash function and what are the different types of hash functions. So suppose if I want to store an element 5 and size of the array is 6 for me, that is I have 0 to 5. So these are the indexes which I have, empty locations initially. So I want to store an element called as 5. Element 5 will be passed as an argument to a particular hash function, and this will generate an index, and based on that index this element 5 will be stored for you. Okay, so that is, and why do we study this, and what is specialty about this is, key itself generates the index at which it has to store, and retrieval also happens in such a way. We'll see an example and we'll clarify it. And search operation takes hardly one comparison here. Okay, there are exceptions, but here searching an element, once you are stored using a particular hashing technique, you have stored all the elements, then retrieving them also doesn't take much amount of time. It takes hardly one comparison in an ideal case. And let us see what are the different types of these hash functions which are used by us. So these are the different types of hash functions which we use. We'll see each and everything one by one, and with example we'll see how we proceed. So first we'll talk about division method. In division method, so our hash function is x mod m. What we had done is, suppose m is the hash table size, that is your array size. In this you have to store all the elements. As usual, array index starts from 0 and ends at 7. Suppose if you want to store an element called as 4, which is an hash key. If you want to store an element called as 36. Okay, so which is a key for you. What do we do is, we apply percentile operator for this key, and we apply modulus, that is, we say that 36 mod 8, where 8 is the size of the table, that is size of your array, and 36 is the key or the element which you want to store, and 36 percentile 8 is 4 for you. At index 4, element 36 will be stored for you. Okay, so what I have done is, I am saying that there might be a list of elements which can be generated. Okay, and all these elements has to be stored in a particular memory, and the memory is organized in the form of an array, and in an array every memory has an index associated with it. And if I want to store a particular element, I mod it with the size of your table, and whatever the result which I get will be the index at which I will be storing the element. Okay, so similarly you have an element called an 18 which has to be stored. Same process, 18 mod 8 is 2 for us. At index 8, 18 gets stored. Next you want to store an element called as 72. 72 mod 8 is 0 for you. At 72 gets stored at 0th index. Then you have 43. 43 mod 8 is 3 for you. At index 3 this gets stored, 43 gets stored. Next you have element 6. 6 mod 8 is 6 itself. At index 6 the element gets stored. So all the elements are stored in your, so we have had to store 5 elements, and all the 5 elements are stored in the memory locations. Next, how do you want to search for this? So what makes this data structure special, or what makes hashing so special? Suppose if you want to search for an element called 72, I know that. So what are the prerequisites for this? For searching the element 72, I know that size of the table m is 8 for me. And I know that what is the modulus function which I have used. I have used division method. In division method I know that I will be usually applying x mod m, that is the key mod the size of your table. So to check whether where 72 is stored, I apply 72 mod 8. So 72 mod 8 gives me 0, so I immediately go to the index 0, I get the element, and if the element is not available there, that implies that element is not available in the array itself. So as you can see, searching becomes easier. So the way in which you store the data is the way in which you retrieve the data. Okay, so you generate an index using the element itself, and for searching also you generate the element index using element itself. So unlike in an array, usual array, what happens, suppose these are the numbers you have in your array. If you want to search for an element 3, okay, so you don't know where 3 is available in this array. So first we check whether 5 is equal to 3. If this condition fails, you increment, then you check 1 is equal to 3, fails, then you say 3 equal to 3, condition satisfies. So that is, you have a for loop for I equal to 0 to n minus 1. You check if key is equal to a of I. If it is not, you escape. If it is, you print the element. Okay, so this is the logic. So here you see there are a lot of comparisons for us, but here what we have done, without any comparison itself, using the key itself, we identify the index where it has to be stored. Okay, so that is what we have done. So that makes hashing special. That is, searching becomes way more easier when compared to an array or a linked list or a binary search tree or binary tree or AVL tree. Okay, because the key itself is involved in generating the index for us. Okay, so this is, now we will be seeing different types of hash functions. So this is a division method. Now in the other methods, this function will be varying for us. Okay, but the main logic remains is we will be using the key to generate an index. Okay, and the function varies for us. So this is another example for your hash table collision, that is your division method. So, and here the hash table size is 11 for us. So 93 mod 11 is 5, so 93 gets stored here. Next you want to show element 61 mod 11 is 6. Okay, so at element 6, 61 gets stored. Then you have 48 mod 11, that is next element is 48, 48 mod 11 is 4, so 48 gets stored in index 4. Then you have 77 mod 11 is 0 for you, so at 0th index 77 gets stored. Then you have 54 mod 11 10, so at 10th index element 54 gets stored. Next you have 75 mod 11 which is 9, so 75 gets stored here. Next element you have is 42, so 42 mod 11 is 9. Okay, now we have a problem. Already at 9th index we have an element called 75, and at this point we have got an index 9 and we want to store element called 42. Okay, so this is what we call as a collision. So when two elements are competing for the same index, collision happens. And how to resolve it, there are different methods for resolving it. So where we cannot discard the element 42, right? So 42 has to be stored somewhere here. So where 42 will be stored, we'll see those things in our next part. Okay, that is how to resolve collision. So there will be collision resolving techniques, different types of collision resolving techniques. We'll see how the collision is resolved. So obviously we know that in hashing, what are the facts which you have understood till now? In hashing, obviously we have to know the hash function. Okay, to this hash function we pass the key, and once the key is passed to the hash function, we generate the index where it has to be stored. And for searching also the same process continues. Okay, that is, you apply the same hash function and pass key to it, and index, what index comes, that will be the element to be searched. Okay, and also there will be a concept of collisions for you. Okay, so you also have the concept of collisions occur when we have more than two elements competing for the same index, and for this we have various types of techniques which will be studying. So this is another type of hashing method. So that is, we change the hash function here. Instead of using modulus operator, what do we do is, the key which you want to store, that is 93, here what do we do is, in this hash function we specify something called as r digits. Okay, I'll tell you in a minute what do you mean by r digits here. So first let us look at the process. You want to store element 93. First you square 93, that is, you apply square operation. 93 square is 8649 for you. In this 8649, what do you do is, you take middlemost r digits. Okay, here the value of r is 2 for us. Okay, so we consider only the middlemost two digits of the squared number. Okay, so what do we do? Given a key, given an element, we square it and we take the middlemost r digits of that number. Okay, and whatever the number which you get, if this value is greater than, if this value, okay, is greater than the index, you apply mod operator. Okay, that is what we have done here. So this value is greater than the size of your hash table, that is your array, that is your m size is 11, and key which you got is 64 mod 11 is 9. So at 9th index your element gets stored. That is the process. That is, if you look at take another example, you have an element called 61. So 61, you apply 61 square, you get 3712, you take middlemost two digits and you get the value 72, which is greater than 11. You apply 72 mod 11, which is 6. At index 6 element 61 gets stored. So there might be a doubt, like suppose if you square a key value and you get an odd number, that is, if you get this is a number which you have obtained and for some x key. Okay, so and r value is 2 for you. So which value you have to consider? So it's up to you, either you can consider 72 or 21, doesn't matter for us, but you have to know which one you have considered. That is, if you are considering the first two digits, then you have to follow the same rule for all the elements. Okay, all the elements of the same digits. Okay, and if you are following 21, you also have to follow the same rule for all the elements of the same digits for you. Okay, so next time whenever you search for an element, obviously you will be getting again 3x square will be 3712 for you, 16, and you know that you consider first two digits and you go to the particular index and you search for that element. Okay, so this is a mid square method for you. That is, given a key, you apply square for it and you take middlemost r digits of it, and if that value is greater than the hash table, you apply modulus operator of it. Okay, so this is mid square method. Next we have folding shift method. That is, this is a new hash function for you. Usually this folding shift method is used to store large values like mobile numbers, etc. For example, you have ISBN numbers. Okay, so usually books, journals and any papers you submit have ISBN number associated with it. Usually this ISBN number are of this form. So what do we do is, if you want to store such kind of ISBN numbers in a database, and usually obviously this will be, if it is stored in a database, people will be trying to search for some particular book or some particular ISBN number. At that point you should take less amount of time retrieving the journal or the book which you are trying to search. So for this, what do we do is, whenever given large values, and if you want to store the large values in an array, you use fold shifting method. This fold shifting method, what you do is, given a number, suppose for example 3205 is given to us, you break them at some particular point. So suppose two digits each, you break them. So you then, after breaking them into 2 digits each, you add both of them. Okay, the value which you get is 37. Okay, and if this value is greater than the table size, you apply mod operator for it, and the value which you get is 3. At index 3 element, that 3205 will be stored for you. And if you want to retrieve 3205, if someone is searching for an element called as 3205, how do you do that? We know that we have divided this number into 2 digits each. We know that, we have to know that, otherwise you cannot retrieve it. So we know that we have divided them at 2 digits, so we also do the same thing. So we get 37 mod 11 is for us 3. So we go to that index 3 and we retrieve the value for us. So usually this is used for showing huge numbers. Okay, and this is also considered one of the better hash function when compared to all the other hash functions, because all the digits in the key participate in generating a index value. So here previously only less number of keys were participating, but here mostly all the keys participate in generating a index value for us. Okay, this is fold boundary method. In this fold boundary method also the same logic follows, that is we divide them at some particular digit. That is, here we have considered 3 digits each. We have, because it's a very huge number, so we considered we have considered 3 digits each. Then what do we do is we add them similar to your fold shift method. Okay, but only difference is we have to either the last one or last second one, or the one, either whatever one of the digits should be flipped for us. That is, for example, for fold, if you apply fold shift method on this method and you divide this number at every 3 digits, so the value will be 1 2 3 4 5 6 7 8 9. Then you add it up. Okay, this will be a fold shift method. But in the fold boundary method, what do we do is either we flip reverse any one of these 3 digits here. So here what we have done is we have reversed the middlemost value, or we can also reverse the last value. So any one of the 3 digits has to be reversed. Then you add them up, and whatever the index which you get, at that index you store this value, the very large value which you have obtained. Okay, so this value, if it is if the generated index is greater than the table size, you apply mod operator on it. So this is about fold boundary method. So it is similar to fold shift method, but only thing is one of the number which you have divided should be flipped by before adding. We also have the concept of truncation method. In truncation method, it's a simple form. Given a value, you truncate at some point. Suppose, for example, here I said that I'll be only considering the last 2 digits of the given number, and I'll be applying modulus operator on it, and whatever index which I get, at the index the value 27869 will be stored for me. Okay, either you can divide them at last index, last second index, last third index, last fourth index, or the entire number can also be divided. If entire number is divided, then it becomes a division method. So for that, what do we do? Given a very huge number, we want to quickly store them, you only consider some parts of that digit and you apply modulus operator on it, and whatever the index which you get, at that index you store the value here. So obviously this is not considered a better option for you, because here only few digits participate in key generation. So what do you mean by only few digits participating and all the digits participating index? It implies that, remember, we have the concept of collision here. Okay, so if all the digits in a number participate, we have less number of collisions. That is what I meant to say. Okay, here in mid square method, in fold shift method or fold boundary method, we say that number of collisions will be less when compared to all the other methods. So that is why we say that both the methods are better than other hash functions for us, or other methods in the hashing. Okay, so whichever method produces less number of collisions is a better option for us. Okay, better option for storing the data, better option for hashing itself. Okay, so this is truncation method. Let us take an example. Here the question is calculate the number of collisions occurred when the following keys are stored in an hash table. Size of the hash table is given, which is 13, and these are the keys which has to be stored, and we are asked to use division method. Okay, so what do we do is these are the key elements which has to be stored. So we apply 10 percentile 13, which is 10 at index 10, this gets stored. 100 percentile 13 is 9, index 9 it will be stored, 100 value will be stored. 32 percentile 13 is 6. Okay, so at index 6 the element 32 will be stored. Next, 45 percentile 13, percentile means we calculate the remainder. Okay, So here what do I mean by here is 32, how do you get 6 here is, you say that 32 percentile 6, so 6 4 ja 24, okay, or you can simply, that is whatever the remainder which you get, that is 32 percentile 32 percentile 13 you have to apply, okay, and 13 2 ja is 26, so 13 2 ja is 26 for us, and the remainder which you have is 6. So that is what I meant by percentile operator here, okay. So 32 percentile 13, the table size is 6, at index 6 32 gets stored. 45 percentile 13 is also 6 for us. Now what we have happened is, at index 6 already element 32 is stored, and 45 is also trying to compete for the same position, so we say that one collision has occurred for us. Similarly 58 percentile 13 is also 6, second collision, that is at the same position, all at the same index, all these positions are trying to get into, but we are not trying to resolve them, but we are just calculating what are the number of collisions which occurs. 126 percentile 13 is 9 for us, but at index 9 already we have an element called as 100, so this is a third collision for us. Then 3 percentile 13 is 3, there is no, previously there were no elements stored there, so at index 3 element 3 will be stored. 29 percentile, that is, if you want we can have a table here. So 10 percentile 13 is 10, so at index 10 gets stored. Then 100 percentile 13 is 9, so 100 gets stored here. Then 32 percentile 13 is 6 for us, so here 32 is stored. 45 percentile 6 is 45% 13 is also 6, so 45 tries to get here, so one collision. 58 percentile 13 is also 6 for us, so 58 comes here, there is a collision here. So we are not trying to resolve it, but we are just calculating the number of collisions. 126 percentile 13 is 9 for us, but at 9 already we have 100 element called as 100, so 126 is trying to get here, so this is our third collision. 3 percentile 13 is 3, so at element here the element 3 gets stored. 29 percentile 13 is also 3 for us, so this is our fourth collision. 29 is trying to get here, so 1 2 3 4, you have 4 collisions. Then you have 200 percentile 13 is 5, so at index 5 200 gets stored. 400 percentile 13 is 10 for us, at index 10 again 400 is trying to get into, okay. So then 0 percentile 0 is 0 for us, 0 gets stored here. So how many collisions do we have? 1 2 3 4 5, so we have total of 5 collisions. Okay, so this type of questions can be asked for you, okay, to calculate number of collisions using different methods here. So let's take another example here, the same thing, so you can use the same method for calculating the number of collisions here, but what we are doing is, by here we are using fold method. So what type of fold method is given to us here? We are asked use a fold method where individual digits are added together and we reduce it to the hash table size. That is, if individual bits are reduced, that is what we mean with, suppose if you want to store element 10, individual we add individual digits, so 1 plus 0 is 1 for us, and 1 percentile size of the table is obviously same size, that is your 13, so 1 percentile 13 is 1, so at index 1 the value will be stored for you, okay. Now if this index value, if it is greater than the table size, then you apply modulus operator, that is what you mean by reduce it to the hash table size, okay. And 100%, so if you, the same thing, if you want to apply the same logic on the value 100, so 1 plus 0 plus 0, so 1 plus 0 plus 0 is 1 for us. So at index 1 again you are trying to store an element 1, so you have one collision here. 32, so 3 plus 2 is 5, at index 5 it gets stored. 45, 4 plus 5 is 9 at index 9. Then you have 58, 5 plus 8 is 13, 13 is greater than the size of the table, that is 13, so size of the table also 13, so it is greater so it is not equal to, so greater than, so what you do is you apply 13 percentile 13 at 0 index, you store the element 13. So the whatever the value which you generate, whatever the index which you generate, if it is greater than, okay, the table size, obviously you have to apply modulus operator. And next you have 126, 1 plus 2 plus 6, so 1 plus 2 plus 6 is 9, 9 is less than 13, so at index 9 you store the element 126, but at index 9 already 45 is stored for us, so you have second collision. Then element 3 percentile 13 is 3, no problem. 29 percentile 13 is 11, no problem. Okay, and next you have 200 percentile 13 is 2, no problem. 400 percentile 13 is 4, no problem here for us. Okay, so obviously, so 0% 0, so at index 0 already you have you already store an element. Okay, so that is the 58 gets stored at index, and 0 also wants to compete for it, so you have 3 collisions. As you can see here, previously you had 5 collisions, but here you have only 3 collisions. That is, in fold method, number of collisions will be reduced for us. So our main aim in hashing is, so we know how to store an element and how to search for an element, but we have to reduce the number of collisions, and for that we use different types of hashing methods. Okay, now we'll talk about different types of collision resolution techniques. That is, when a collision occurs, what has to be done. So there are 2 methods which can be followed. That is, one is open tracing, another is chaining. In open tracing we have different methods, that is linear probing, quadratic probing, random probing, and double hashing. These are different methods which can be used. So what do I mean by that is, suppose for example here, if you look at, let us look at a small example of linear probing. Element 10 has to be stored, so you apply division method. So 10 percentile 13, so 10 percentile 13 is 10, so at index 10 the element gets stored. Next you have 100 percentile 13 is 9, so 100 gets stored. Next you have 32 percentile 13 is 6, at 6 index element gets stored. Now as you can see, 45 percentile 13 is also 6 for us, but at index 6 already we have an element called as 32. So here one collision occurs. So what we have done is, whenever in linear probing, whenever we are using linear probing to resolve a collision, we look for the next immediate free memory location. Okay, and if you have a free memory location, you store the element, whatever the new element which you have obtained. That is, here 45 also is trying to get into the index number 6, but already 32 is available there. So I immediately look at the next immediate free memory location. So next immediate free memory location was 7 for me. At 7, 45 gets stored. So it doesn't create any problem for us by searching also. Suppose for example, if you are searching for an element called as 45, we know the size of the table and we know the division method is used. 45 percentile 13 is 6 for us. We immediately come to the index number 6, but at index 6 element is not available immediately. And also we know that we have whenever a collision occurs, we use linear probing for this table. So in linear probing, what happens is, I have to look for the next element. I say that if element is not available here, it might be, there is a possibility that there might have been a collision and the element is stored in the next memory location. So what will happen is, I search for the next memory location. So on, I will be searching the entire table until I come back, unless I again return back to the index 6. Okay, if I return back to the index 6, that implies that element 45 is not available, otherwise I find that element. So that is the logic. So similarly, you have the element 58 percentile 13 is 6 for us. So 58 first tries to get here, already element is available. Next it comes to the next free memory location, element is available. Next what happens is, it comes to the next free memory location, which is 8. So 58 will be stored here for us. Next you have 19. So 19 percentile 13 is 6 for us. So 19 tries to get into here, already occupied, comes to the next free memory location, already occupied. Go to the next memory location, already occupied. Go to the next memory location, already occupied. Go to the next memory location, it is also occupied. So next free memory location we have is 11. So at index 11, element 19 will be stored. So this is what we meant by linear probing. Next, we have the concept of quadratic probing. Okay, so here we try to resolve the collision in a different way. That is 10 gets stored at index 10. Same thing, that is size of your table is 13 and we use division method. Okay, so 10 percentile 13 is 10, so 10 gets stored here. 100 percentile 13 is 9, so 100 gets stored here. So you have element 32, so 32 percentile 6 is 32 percentile 13 is 6, so the element 6 gets stored here. Next you have 45, so 45 percentile 13 is also 6, so we have a collision. Okay, so whenever a collision occurs, so 45 is also trying to get here. So now what do we do is we follow this algorithm. What does this algorithm does is, you start with an arbitrary I value as 1 and you do this operation. So here key value is 45 which you want to store, and 43 percentile 45% of 13 is 6, which is the h value for it. So index is h. Okay, so what we have done is, I start my for loop. For I is equal to 1, I calculate h is equal to 6 plus square of 1. 6 plus 1 is 7. So what do I do is, I look at the next immediate free memory location. So it was free, so 45 got stored here. Okay, so 45 got stored here, so no problem. Similarly, next element is 58 for you, so 58 has to be stored here. So when 58 has to be stored, the same thing, that is 58 percentile 13 is 6, so h value is 6 for you. Then you start with your loop, I is equal to 1, 6 plus square of 1 which is 7. You go to the index 7, 7 is already occupied, I value is incremented according to our algorithm. Again h is equal to 6 plus square of I, that is square of 2. So square of 2 is 4, 6 plus 4 is 10, and index 10 is also occupied for us, I value gets incremented. So h is equal to 6 plus square of 3, that is 9. The value which you have got is 15, which is greater than the total size. Whenever the index is greater than the size of the table, we apply mod operation. So 15 percentile 13 is 2 for us, so index to 58 gets resolved. Okay, so this is what you mean by quadratic probing. And why do we do this is, why do we have the concept of linear probing or quadratic probing is, in linear probing what happens is, if you apply linear probing, more number of elements will be, similar type of elements will be scattered at some particular memory locations. There is more number of collision will be occurring at only one part of your complete hash table. Okay, and this is called as primary clustering. And in your quadratic probing, what happens is, you will be having lot of primary clusters, that is more number of collisions will happen in this part, and also more number of collisions will happen in this part. So at different memory locations, for set of some memory locations, there will be lot of collisions for. Okay, so that will be our next video, where we will be talking about what do you mean by primary clustering, secondary clustering. But for now, remember that linear probing leads to primary clustering and quadratic probing leads to secondary clustering. That is, in your primary clustering, there will be lot of, that is usually indexes which gets generated. All these indexes will be related to only some part of your hash table. Okay, and in your quadratic probing, whenever a collision occurs, a new index will be either related to this part of your data, this part of your data, this part, or this part. That is, it gets grouped at some part. Okay, collisions are grouped together at some part, so that should not occur and we should avoid it. And we talk about double hashing. In double hashing, whenever a collision occurs, we apply another new hash function to it. That is the concept here. So 10 and 20 get stored, there is no problem here. Size is the size of your hash table is 7, and we are using division method. So 10 percentile level is 10, 20 percentile level is 9. So these two get stored here, no problem for us. Next you have 17 percentile 11 is 6, so it gets stored at index 6. Next you have 28 percentile 6, 28 percentile 11 is also 6, and 28 is trying to fit here, so there is a collision. So when a collision occurs, what do we do is, this is our first hash function. So we have got an index y, and whenever a collision occurs, we apply a second hash function, and after applying second hash function, we calculate the index value for it. So what we do is, suppose here 28 is a new element, 28 percentile 10 is 6 for us, we have a collision. So index is taken into variable called as y. We apply second hash function. We pass this value to second hash function. In your second hash function also the same. The element key 28. Here 7 is a prime number. Okay. So usually it is less than. We consider a prime number less than the table size. Usually we do this. Okay, but because having such kind of criteria reduces number of collision, that is an observation. Okay, 7 is a prime number which is less than the table size. So we say that 28 percentile 7, which is a prime number, plus 1, this is our formula, equal to 1. Okay, we have generated a value which is 1 and we call it as C. So we have variable called y and we have variable called C, and we pass it to the third equation which calculates the index. So the new index is 6, that is your old index, plus next you have new index percentile the size of the table. So why do we do this? To just to clarify or just to see whether if the total addition increases the size of the table or not. So new index, wherever the old index, so old index has caused the collision. So for that what we do is we calculate the new index value, and if the total size is greater than the hash table, then we apply percentile operator. That's it. So and the new index has obtained at index number 7, element 28 gets stored for us. So in double hashing, whenever a collision occurs, we try to calculate the new index where it can be stored by using another hash function. So this is another example, 39. If you want to store an element called 39, so the same thing has to be followed. Here what we have done is here at index 6 collision has occurred. This is your old index. Next you see that you pass it to the second hash function. So same key, prime number, and plus 1, which is 5, which is a new index, which is a new value for us. So new index is calculated as old index plus the other value which you have calculated from the C value which you have calculated from the second hash function, percentile 10, size of your hash table, which is 11, and 11 exceeds the size of your table. So 11 percentile 10 is 0 for us. At 0, 39 gets stored for you. So it is the same process in which the 39 will also be retrieved. So in the same table, if you want to search for the element 39, same process has to be repeated. So you have to know the first hash function. You also should know the second hash function, and you also have to know, you have used the concept of double hashing, and the size of the hash table should also be known to you. So if whenever you are talking about this hash data structure, all these things has to be known for, that is hash function, then what type of probing we have used, table size. So all these things has to be known by the user when he is searching for an element. Okay, then we come to the next part, which is your chaining. In chaining it is simpler, that is whenever you have a collision, you create a list and you attach that element to that index number itself. So you want to store an element called as 10, the index is 0, we have used division method. So at index 0, 10 gets stored. Okay, similarly 5 percentile 5 is 0 for us. So we have a collision, you create a new node and you attach it to it. 50 also creates a collision, create a new node attached to it. 15 also creates a collision, create a node attached to it. 45 also creates a new collision, create a node attached it. So whenever a collision occurs, what do? Is we create a list and we attach that collision, the collider nodes together. Okay, and we also, when to increase its performance, we also sort all the elements which are attached to a particular index here. So searching becomes easier. So this is the method of chaining for us. Okay, so these things we'll be talking in next videos, that is your primary clustering, secondary clustering, and random clustering. That is in a hash table, if more, so suppose this is your index numbers. In primary clustering what happens is, whether you're using linear probing, quadratic, or hash function, double hashing, all the new index values will be all the new index values which gets generated will be attached to a particular set of memory locations. That is, every time a collision occurs and you try to calculate the new one, the new index will be this. So there is a high probability that new index value will belong to a small subset of the total indexes available to you. Why is this a problem for this? This creates a lot of collisions. Every time only this index values get generated and all the values are clustered here, and this creates more number of collisions for us, and after lot of permutations and combinations we move out of this and we find a empty location outside this. So this is a primary clustering. In secondary clustering means such type of primary clusters occur at different parts of your hash table. Random clustering is randomly at some part your cluster you either have you have this sort of clusterings. Okay, so if you take an example, so you have the index values. Suppose if you want to store a value called as 28, so 28 percentile some value, so 28 percentile 28 gets stored at index 0. You want to store element 29, 29 gets stored here. Similarly, again if you want to store 38, 38 also generates index 0, you have a collision 0. So what you do is you use either linear probing. Okay, so you either use linear probing, or you use quadratic probing, or you use double hashing. Whatever the techniques which you use, the techniques will be either generating 0 or will be generating 1. That is, they will be either generating 0 or 1. So for most number of combinations, that is more number of times, either 0 gets generated, 1. So you will be using, you have to apply linear probing, quadratic probing, double hashing more number of times, then only you will be getting an index which is outside 0 or 1. So more number of collisions and more number of new index values occur at this point here itself. So this is a primary clustering. Such type of situation, if it occurs at more memory locations, so we call it as secondary clustering for us. So with this we come to an end of the concept of hashing. Okay, so let us next video we will be talking more about this.